Okay, so we'll start the class now. So today we'll see what are various stresses develop in case of the screw joints, threaded joints, or bolted joints. All these three are same. Don't think that screw joint or fastening is different, or bolted joint is different, or threaded joints is different. Whatever name by it may be called, whether it is screwed fastening or screwed joint or threaded joint or bolted joints. All these are same. So now we'll see what are various stresses when these screwed joints are subjected to static loading. So we are not discussing about the static loading. We'll discuss about only static loading because that is only static loading part is there in our included in our syllabus. Fluctuating loads or static loads are not included in our syllabus. So we are not going to discuss about design of the screw joints under fluctuating loads. Okay, right. So now, if I want to see the stresses, or if I want to find the stresses in case of any screwed joint or bolted joint, like what we discussed in the previous class, so there are two cases or two instances the screwed joint is subjected to the load. One is we call it as stresses due to initial tightening. So that's what I written. The following stresses in screwed fastening due to static load are important. So one is the internal stresses due to screwing up forces. So we call it as internal because it is while forming the joint. So here it is called screwing up forces, means tightening of the joint. So by tightening of the joint, there are stresses will induce in the joint. So those stresses will treat those stresses as internal stresses, and we also call this one as stresses due to initial tightening. So both are same, internal stresses due to screwing up forces or stresses due to initial tightening. So that means before applying the external load on the joint, so because of the tightening of the joint, there are some stresses which will develop in the joint. So those stresses we'll call it as internal stresses, and we'll see how we can calculate those stresses one by one. And what are the stresses? What are the internal stresses which are going to induce in case of screwing up forces or in case of initial tightening? We'll see that, and now we'll also see how we can calculate the magnitude of those internal stresses also. Then the second one is stress due to external forces, that is, or external loads. It need not be always force. You may have other type of load also. So we call it as stresses due to external loads. So that means when a joint is subjected to external loads, so that means the load which is not part of your initial tightening, then we'll call it as a load as an external load. External load may be either in the form of a tensile load or it may be a twisting moment or torsion moment. So then because of this externally applied loads, so the stresses will also induce in this bolted joint. So then we need to find out the magnitude of those stresses also. So then next is combination of these two. That means when there is an initial tightening as well as the bolted joint is subjected to some sort of external forces or external loads also. In that case, you have a combination of these two, that is stress due to screwing up forces plus the stress due to external forces. So like this, you have three different categories. One first category is when the joint is subjected to only initial tightening. So then what are the stresses? So those stresses we'll treat them as a internal stresses, and we'll see in the next slide, we'll see what are those internal stresses and how we can calculate the magnitude of those internal stresses. Next one is stress due to external forces. That means in case of the second case, we'll assume that there is no initial tightening or no internal stresses in the joint, and we'll calculate the stress due to only external force. Then the third one is combination of these two, that is, we'll consider both initial tightening load as well as the externally applied loads. So then we'll find out what is the magnitude of the stresses because of this combination of loads. Okay, now we'll see what are various stresses developed due to initial tightening or due to the screwing up forces. So first we'll see this, then we'll move to this one, and then finally we'll look at it to the third case also. So first, if I go to the internal stresses due to screwing up forces. So in that first one we will call it as a first stress is going to be the tensile stress. Whenever if you tighten the nut, so because of the tightening, then what happens is the bolt will try to elongate. The bolt will try to elongate. So because of the elongation of the bolt, it is subjected to a tensile stress. So now how we can calculate the magnitude of this tensile stress? That we already know. Tensile stress is nothing but load. What is the initial load on the bolt? Or what is the load due to this initial tightening divided by the tensile stress area. So from that you can get the tensile stress. So that's what written in this slide. So since none of the above mentioned stresses are accurately determined, so that means here we categorize the stresses into three categories. Those are one is internal stresses, the other one is the stresses due to external forces, then the combination of stresses due to these internal loads as well as external loads. So in case of bolt, so exact estimation of this magnitude of these stresses is difficult. Why? Because you have a threaded portion. So in case of bolt or nut, if you take, you have a threaded portion, something like this. So here this threaded portion will create some sort of stress concentration, and also not only that, we are taking to calculate the tensile stress area, we are taking the average, that is dP plus dC by 2, average diameter of dP plus dC by 2. So this is only also an approximation only. So only thing is, based on the experimental results only, people are arrived at, you need to use this diameter for calculating the tensile stress area, that is nothing but dP plus dC by 2. So therefore all these are empirical relations, or we can say that approximate relations. So because of this, it is not possible to calculate all the stresses, exactly. So therefore they are approximate stress values only. So but while designing a joint, if you design it for an approximate stress value, you never know whether the joint is safe or not. So therefore, in order to avoid the failure, here people will use a large factor of safety. So with large factor of safety, what happens is, even though you are not estimated the magnitude of stress exactly, so then in order to safeguard against the failure, this large factor of safety will be used. So that large factor of safety will safeguard the component even the stresses are computed, whatever magnitude of the stresses computed which is not accurate. So that's what I written here in this particular slide. So since none of the above mentioned stresses are accurately determined, I already told what are the reasons for that, why we are not able to calculate accurately these stresses. Therefore, bolts are designed on the basis of direct tensile stress with large factor of safety in order to account for indeterminate stresses. So that means indeterminate means the stress which are not determined. So sometimes it is not possible to calculate all the stresses in case of bolts. So therefore, to accommodate or to account for those indeterminate stresses, so a large factor of safety can be used so to accommodate these stresses. So that means, so most of the cases, if you look at any bolted joint, the design is based on only tensile stress, even though it is subjected to different types of stresses. So the design is only based on tensile stress. That means all other stresses were ignored in the design just by considering the large factor of safety. So that means, so now onwards, whenever you have a design problem on this bolted joint, so we need to look at only on the tensile stress. But the thing here is, even though we are looking at the tensile stress only, first we'll try to see what are various stresses developed in the bolted joint because of this initial tightening, and then later, if they are absolutely necessary to include in the analysis, we'll consider. Otherwise, we'll ignore those stresses and we'll consider only the tensile stress with some factor of safety. Okay, so the initial tension in a bolt based on experiments may be found by the relation. So this we already discussed in the previous class. I already showed it to you in the data book also. This relation is there in the data book also. That initial load or load on the bolt due to initial tightening is given by 2840 into D, where D is the major diameter or nominal diameter of the bolt, which should be expressed in terms of mm only. So that means suppose I have a M20 bolt is there with me. So that means 20 is the nominal diameter for the bolt. So now I want to find out the initial tension in the joint because of the tightening of the joint. So again here there are two types of joints. One will call it as a fluid tight joint. Other one is non-fluid tight joint. So this relation P1 is equal to 2840D is holds good in case of only fluid tight joint like steam engine cylinder cover joints. So if it is a non-fluid joint, then your initial tension in the bolt is going to be only half of this value. That is half of 2840 will become 1420D. So that I should also. So that means, so here, see, I already told you. So this is also based on only experiments. We never know exactly because of the initial tightening, this much load is going to act on the bolt. So that means this is a empirical relation only people are using, but this is not. It may be the actual load on the bolt may be more than this or maybe the less than this. So this is only this relation is based on the experience or based on the experiment results only people are using this. So like we said in the previous statement, so to cover up that or in order to accommodate any uncertainty in this load, we are using a factor of safety to cover the uncertainty in calculation of this load. Okay, so once you know this, that is initial load or tensile load. So this P1 is nothing but the initial tension in the bolt. Then D is the nominal diameter. If you know the initial tension, then the tensile load divided by the tensile area of the bolt will give you the tensile stress. So then when the joint is not required as tight as fluid tight joint, that means if the joint requirement is not a fluid tight joint, so that means non-fluid tight joint, then the initial tension in a bolt may be reduced to half of the above value. The initial tension in a bolt based on experiments may be found by the relation. So now the initial tension, if the joint is a non-fluid tight joint, it is going to be only half of the previous value. Earlier you have here 2840D, now it is only 4220D. So that is 1420D is going to be the initial tension while you need to consider while taking if the joint is a non-fluid tight joint. So then, and also here one more point what you need to remember is whenever a bolt is subjected to initial tightening, so it is subjected to, that's what we are discussing, it is subjected to various stresses. If the bolt diameter is less than 60 mm, that is the nominal diameter is less than 16 mm, so it is going to fail for a fluid tight joint. That means for M16 you have a tensile stress area. So what is the tensile stress area for a M16? Why you cannot use smaller diameter bolts for fluid tight joints? The reason behind is, so if you open your data book, so for M16, what is the tensile load? What is the tensile stress area? If I refer the data book here, in the data book, the tensile stress area is going to be only 157 mm square. So if you have a data book, you can refer the tables what I have shown in the earlier class. You can refer that. In case of M16, its area is tensile stress area is 157 mm square, whereas for M18 it is 192 mm square. So that means here, so generally the bolts are made of mild steel, so it has some allowable tensile stress. For mild steel, that is around 300 MPa, you can take it as allowable tensile stress, or maybe depending upon the composition, you can take that. So now, if I take fluid tight joint here, the initial load on the bolt tight joint is going to be 2840 into D, that is 2840 into 16. If I take M16, it is into 16 here. I need to take, I'll get a load divided by its area. Our stress is going to be more than the allowable stress. So that means the joint is going to fail. So that's what he written. Smaller diameter bolts may fail due to tightening. So therefore, bolts of smaller diameter which are less than M16 are not permitted in making fluid tight joints. So this conclusion is arrived based on only the initial load. Here, initial load is going to be for fluid tight joint is 2840 times D. So the D is, if I take M16, let us say it is 16. So this is going to be our load divided by the area, that is 153. For M16 it is, the tensile stress area is 153. If you compute this, the stress, whatever stress you get it here, the magnitude of the stress is more than your allowable stress. The magnitude of the stress, whatever you get due to initial tightening, is more than the allowable stress. So therefore, the bolt will fail because your stress induced is more than the allowable stress, means the component will fail. So that's why a bolt which is less than 16 mm nominal diameter cannot be used for making fluid tight joints. So this is another point you need to remember. So then, even though I am not given the formula here how to compute the tensile stress, we know that the tensile stress is nothing but sigma is nothing but our load, that is P1. Load due to initial tightening is P1, whether it is fluid tight joint or non-fluid tight joint. If it is a fluid tight joint, you need to take P1 is 2840D. If it is non-fluid tight joint, you need to take P1 is equal to 1420D divided by AT, that is the tensile stress area. So the tensile stress area, you can take it from the data book corresponding to the nominal diameter, whether it is M16, M18 or M20, whatever may be the given value. So from that you can pick the AT value from the data book, then you can compute the tensile stress, which is given by load due to initial tightening divided by the tensile stress area. That is the formula to compute the tensile stress due to initial tightening. Then we have torsional shear stress. Why we have a torsional shear stress? Because we are tightening the bolt, so therefore we need to apply some initial torque. So during the tightening, you need to apply the torque. So the torque is transmitted through as a frictional resistance of the threads. So because of this frictional resistance of the threads during tightening, there is a torsional shear stress. To compute the torsional shear stress, or the torsional shear stress is caused by the frictional resistance of the threads during its tightening, is obtained using our torsion equation. We know the torsion equation, that is T by J is equal to tau by R. So using that relation, you can easily calculate the torsion shear stress. How is the torsion shear stress? T is the applied torque and J is the moment of inertia, polar moment of inertia of the bolt. So here important point is, while calculating the polar moment of inertia of bolt, we need to use the core diameter of the bolt for calculation of J. For calculation of J, you need to use core diameter to compute the J. So because you have different diameters, so here if you want to calculate torsional shear stress because of frictional resistance, you need to use DC for calculating the J value. So, but what is the core diameter? You can use the data book to find. So, if you know the nominal diameter, let us say for M16 bolt, which is a standard one for M16. So, 16 is the nominal diameter. From the data book, easily I can pick the DC value. So now, if you refer the table in our data book, so he has given all the diameters. That is minor diameter. So DC sometimes here we call it as a minor or core diameter. So DC is given as something like in all the threads. So if you look at into those tables, for M16 it is 13.54. 13.54 mm is going to be the DC value. So now you need to use the DC value to compute the polar moment of inertia. But sometimes, suppose for most of the values, all the diameters are for most of the diameters it is available in the data book. Sometimes if it is not available, any standard data is not available for DC. So that means if the information is not available in the data book, then in that case, what we do is we'll take DC as 0.8 times your nominal diameter. So if data available from the data book, we need to take that. Otherwise, if it is not available, only in that case, we'll use this relation to compute DC. DC is equal to 0.8 times D. So this is again empirical relation or the relation which we can also derive it, but we are not looking at the derivation also here. That is also not required because that elastic stress analysis part is not there in our syllabus. So we are not using that, but what you can do is just remember this relation. Whenever there is no standard data is available, in that case we need to use DC as 0.8 times D. So using the DC value, now we can easily calculate what is the polar moment of inertia. Then you can you know how much torque you are applying to the bolted joint for initial tightening. Then from that you can easily calculate the torsional shear stress. So this is the second type of stress induced in the bolted joint because of initial tightening. Then I will go to the next one, that is bearing stress. Okay, so it has shown that during experiments that due to repeated unscrewing and tightening of the nut, there is gradual screwing of the threads which increases the torsional twisting moment. So that means here, whenever the joint is repeatedly used for unscrewing and then tightening. So repeated, if you do that repeating any process, if it is repeating, just this comes under as a fluctuating kind of load. Whenever it is a repeated load or fluctuating load, that means you are tightening and untightening, tightening and untightening. So if you do like that, so there will be a gradual scoring of threads. Means what it is, the threads will gradually wear out. So if they wear out, then the torque requirement will go up. So for tightening, your requirement of the torque will go up because whenever the threads are worn out, the frictional resistance will decrease. If the frictional resistance will decrease, your amount of torque requirement will go on increasing. So that means the magnitude of stress also goes on increasing. So then the third one is shear stress across the threads. So in the previous case, what we have seen is the torsional shear stress due to, here this is a torsional shear stress because of frictional resistance. The third one is shear stress, that is you can call it as direct shear stress also. Shear stress across the threads means it is a direct shear stress. So that is given by the average thread shearing stress for a screw is obtained by this relation. So where tau s is equal to P divided by pi dB into N. So where P is the your torsional load, and then pi DC is the co-diameter, B is the width of the thread at the section where you are calculating the shear stress, and N is the number of threads. So if there are more than one, you need to consider those things. So number of bolts, sorry, not threads, number of bolts. If you have more than one bolt, you need to consider that. So then this is the formula for in case of a bolt. This formula is for bolt. Suppose if I want to calculate for a nut, so here the same formula, only thing is here instead of DC you need to use only the major diameter. That is the only thing. So in case of bolt, the minimum diameter is DC, whereas in case of nut, the minimum diameter is nominal diameter D. So that's why we need to use or we need to replace these diameters accordingly. If you are using this one for bolt, or if you are using calculating the stress in the nut. So only thing is here you have to use DC, here you have to use D. Then next type of stress is bearing stress or crushing stress or a compressive stress. So the compression or crushing stress between the threads may be obtained just by taking the load divided by the bearing area. Always, whenever you are calculating the bearing stress, you need to compute the projected area. So if I take a bolted joint, so the projected area is going to be something like this. If I take a bolt here, okay, let us take this is a bolt. So in this is going to be the threaded portion. You get something like this. This is the threaded portion, and this is the shank portion here. So here, in case of threaded portion, you need to take the shortest dimensions, that is DC. So shank diameter is going to be the outer diameter, and the projected area is going to be something like this. So only you have some hollow circular cross section, something like this. So inner diameter will take it as DC, outer diameter will take it as nominal diameter D. So then the projected area means area of this hollow circular cross section. So load divided by this area will give you the magnitude of crushing stress or buckling stress. That's what is written here. So pi into P into pi d square minus dc square into n. So where d is major diameter, dc is minor diameter, n is number of threads in engage. Number of threads in engage. So maybe in the previous also I said it is number of bolts. It's not number of bolts. It is number of threads only. So number of n is number of threads in engage. So here also you need to consider like that only. So this is the fourth stress, that is bearing stress or crushing stress or compressive stress. Then the last one is going to be the bending stress. So bending stress. So this bending stress only will induce only in particular case, that is when the surfaces under the head or nut are not perfectly parallel to the bolt axis. So that means here generally we'll use bolted connection to connect two members, something like this. This is one member. So and then I want to connect another member to this. This is another member I want to connect. So now if I put a bolted connection here, something like this. So now here I have a nut, something like this here. If this surface is not completely flat surface, suppose here this component is having some kind of inclined surface, something like this. So that means the top component is I have a section something like this, and bottom component is maybe something like this. Now I want to connect this by a bolted joint. So this is the head, and here I will place the nut. So now you see this is having some inclination here, it's not parallel, something like this. So because of this, so you have here head or maybe nut, whatever, maybe either this side or this side, perfectly not parallel. This is your bolt axis. So this surface is not perfectly perpendicular to the bolt axis or not parallel to the bolt axis. Then because of this, this kind of situation is there, then only you have a bending stress. Otherwise, if it is perfectly parallel to the bolt axis, then there won't be any bending stress. So that means you have an inclined surface either on the bolt head side or on the nut side. So because of that, you have a what you can say is bending stress in the bolted connection. So that bending magnitude of that bending stress when the outside surfaces of parts to be connected are not parallel to each other, then bolt will be subjected to bending action. That's what I already shown to you through the figure. Bending stress induced in the shank of the bolt is given by, this is the formula, x into E divided by 2 into L. So where x is the difference in height between the extreme corners of the nut or head. So that means here if you have a surface something like this or surface something like this, so then this height is going to be your x. This is going to be the x. So this corner and this corner. So the difference in the height between these two corners is going to be the x. So either it may be for nut or it may be for bolt head. L is the length of the shank of the bolt and E is the Young's modulus. So now using this formula sigma B is equal to x into E by 2L, you can calculate the magnitude of these bending stresses, right? So like this you can calculate the stresses due to initial load tightening. So we are saying there are five types of stresses will be induced in a bolted joint when it is subjected to initial tightening. are tightening. So what are those stresses? First one is tensile stress, then second one is torsional shear stress, third one is direct shear stress, fourth one is crushing or bearing or compressive stress, and fifth one is bending stress. So now if I take purely fifth one, if the connecting members are having parallel surfaces, the magnitude of bending stress is 0. The magnitude of bending stress is 0. Then if I go to the fourth one, then here this projected area, so it is the magnitude of this crushing stress. I can calculate it like using this formula. Then coming to the third one, here also here you can calculate the shear stress across the threads and also torsal shear stress. Now, if you compare the magnitude of these stresses with respect to your tensile stress, their magnitude may be small, or sometimes we may not accurately compute their magnitude. So in those situations, what we will do is we'll design only based on this tensile stress, and we'll apply some factor of safety to account for the remaining 4 types of stresses. Okay, this is what we need to remember or we need to understand. So always the bolt is not designed based on all these stresses, even though because of initial tightening there are 5 types of stresses induced in the bolted joint. They are not used to design the joint. Only the tensile stress is used to design the joint. So with appropriate factor of safety. Okay, right. So now what we do is we'll take up 2 small problems on this, how we can compute the tensile stress, or how we can find out, if you know the allowable tensile stress, how we can compute what is the tensile load carrying capacity of the bolt. So in that, we'll consider the first numerical problem, that is determine the safe load or safe tensile load. Safe tensile load for a bolt of M30, assuming a safe tensile stress of 42 MPa. So this is the problem, just a simple problem for 2 marks. So what he asked us, find what is the safest load, or that load is tensile load for a bolt of M30. What is the meaning of M30 here? M30 means a metric thread of nominal diameter 30 mm. M30 means a metric thread, and that means the bolt will have a metric threads having a nominal diameter of 30 mm. So for this bolt, so what is the safe tensile load? That means how much magnitude of load you can apply. What is the maximum magnitude of load you can apply such that the bolt is safe. That means it is not going to fail. That means what is the maximum load carrying capacity of this M30 bolt. So for that, what you have to do is first you should know what is the allowable tensile stress. So here he has given that allowable tensile stress is nothing but the safe tensile stress. Safe tensile stress of 42 MPa is given. So now to solve this problem, how will proceed? We know the formula for the tensile stress. That tensile stress for formula is sigma t. If I denote the tensile stress is sigma t, then P by A suffix t is the formula. So that means I should know what is the P value and I should know what is the AT value. So here, since already given the stress value, if I know AT value, I can calculate P. He asked us calculate what is P. What is the safest load on the bolt for this M30. So for that, what we'll do is, from this, if you rewrite this equation, your P is nothing but sigma T, that is the allowable tensile stress or permissible tensile stress or safe tensile stress, multiplied by A tensile stress area, AT. So that's it. If you know this formula, you can easily calculate that. So to compute this P now, sigma T is already given to you, that is 42 MPa. Now only you have to find out AT value. So for that, how you can take the AT value? So you need to open your data book. In the data book, you need to go for the chapter 8. Under the chapter 8, for M30, so generally, if nothing is specified, we use course series. That's what we discussed in the previous class also. If we don't have If you don't, it is not mentioned whether you have to use coarse series threads or fine series threads. We'll use coarse series threads. That is basic series only we'll use. So now you tell me from look at it in the data book and you tell me what is the tensile stress area for a bolt of M30. So now I am posing a question to you. Just you respond to that question. Tell me what is the tensile stress area for a M30 bolt. So you refer our data books and you tell me what is the value for that. Anybody? First, anybody can tell you, or else I'll pick random.
561 mm square, sir.
561
mm square.
561. So if you take basic series, it is 561. That is coarse thread series. It is 561. If we go for fine series, it will goes on increasing. That is 581, 621, 642, and 633. 663. So out of those four values, first we'll take only basic series value. That is 561. So from the 561, using that value, we can compute the stress value. So now I'll go back to the presentation. So that's what I written solution. Given D is equal to 30 mm. D means M30. D means nominal diameter. Sigma D is given as 42 MPa. So then the tensile stress area M30 for M30 bolt is 561 mm square. So this I have taken from the data book. So then the same tensile load is nothing but the tensile stress area multiplied by sigma T. Sigma T is known to you and the tensile stress area is, we have picked that value from the data book. Then just substitute those two values, that is tensile stress area is 561 and the safe tensile stress is sigma T is 42. If you substitute that, we get 23,562 newtons as the safe load on the bolt. That means if the load exceeds this magnitude, then the bolt will fail. Up to 23.562 kilonewtons, the bolt is safe. That means the maximum load, tensile load you can apply to the bolt is 23.562 kilonewtons. So that's it. That is the answer. Straightforward. Only thing is, what you have to do is, from the data book, you need to identify what is this tensile stress area. Once you done that, we get the tensile load. So then we'll take and also here, okay. So in this, okay. So here, this may be this tensile load. So whatever it may be, this load may be either due to initial tightening or this may be combined load or maybe because of both. So, but if this load exceeds this value, then it will fail. So we don't bother whether this is due to initial tightening or due to external load. Only thing is, we are finding out the safe load for this M30. So whether that load may be a combination of initial tightening as well as external load, or it is due to only initial tightening, or it may be only external load. So whatever it may be. Okay, right. So then the next problem. This is also straightforward and simple one only. So here he clearly mentioned that it is due to initial tightening only. So the problem will goes like this. So two machine parts are fastened together tightly by means of a 24 mm tab bolt. If the load tending to separate these parts is neglected, find the stresses that is set up in the bolt by initial tightening. So this is the problem statement. So here in this, the first sentence it is okay, it is clear. So the two machine parts are fastened together by tightly. Tightly means it is a fluid tight joint. You can assume it as a fluid tight joint. Then by means of a 24 mm tab bolt, that means he has given D is equal to 24 mm. Nominal diameter is 24 mm. So that's what we can understand from the first line or first line of the problem. Then he has given that if the load tending to separate these parts is neglected, that means all other stresses are neglected. Only you need to calculate the tensile stress, or only you need to consider the tensile stress. That is the meaning of this one. That means there is no bending, or no shearing, or no twisting. So if that is not there, then find the stress that is set up in the bolt by initial tightening. So because of initial tightening, only there is a tensile stress. Then what should be the stress in the bolt? So that is the question. So for that again the procedure is same. Whatever we follow earlier in the previous case, what he has given? He has given the bolt diameter and he has given the allowable stress. Asked us calculate what is the load. But in this case, what he has given is he has given the load, but he has not given. He has given the value indirectly. Indirectly, he has given the load on the bolt. Asked us compute what is the stress. Formula remains same. Sigma T is equal to P by A. So for computing that AT, that is the tensile stress area, now we need to use M24 bolt. So again from the data book, you need to identify what is the tensile stress area for M24 bolt. So that is, if you use course series, the area is going to be 353 mm square. If you go for fine series, 384, 401 and 418. So there are three series are there for a fine series. You can take those things. But since nothing is mentioned in the problem, we'll take only course series. That is, we'll consider only basic series and we'll pick the tensile stress area as 353 mm square. So that value directly you'll get from the data book. So now once I know the AT value. So once I know the AT value, then if I know P value, I can calculate what is the stress value. So what is the load because of initial tightening? So that we already know there is a empirical relation. So that is given in the data book also. If you remember it, you can straight away use that formula, or else if you are not able to remember those formulas, in yesterday's class I already shown to you how to come, what is the formula for this initial tightening and also what is the formula for the resultant load also. When combination of initial tightening and external load is there, how we can find out the resultant load also. So now we know since it is a fluid tight, so you mentioned it is a tight fashion together tightly means we'll assume it is a fluid tight joint. In that case, the initial load is going to be 2840D. So now we know P value, that is nothing but 2840 into D. D is 24 mm. So you can calculate P value. So from the data book, we already picked the value of AT, that is tensile stress area, which is for a M24 it is 353 mm square. So now you know P value, you know A value. So stress is nothing but P by A. So that's it. So like this you can solve the problem. So now I'll show you the calculation part here. So given D, nominal diameter is 24 mm. Then the tensile stress area for M24 bolt AT is 353 mm square. So you need to pick this value from your data book. Then the initial tension in the bolt P is given by 2840D. This is the formula for initial tension in the bolt. So 2840 into D has given it as 24 mm. You substitute the D here. We get 68,160 newtons as the load on the bolt. So once you have the load, then the induced stress in the bolt sigma T is given by P by AT, which is nothing but 68160 divided by 353, which comes out as 193.08 MPa. That's it. So this is only what you have to do is you need to have only three parameters here. Only one formula you have to use to compute the tensile stress. Sigma T is equal to P by AT. So maybe you will, while designing a formula problem, they will play with these three parameters: sigma T, P, and AT. So of course, by defining, sometimes they will give P value, they will give sigma T value, ask you compute what is the diameter of the bolt. That like that also it is there, but we have not seen that problem. Remaining two kinds of problem we have seen. In the case of first problem, he has given the P value and he has given the sigma T value. So sorry, in the first problem he has given the sigma T value and the diameter, so we can know the AT value. Asked us compute what is P. That is first problem. In the second problem, he has given the P value and AT value, asked us compute sigma T. Maybe third kind of problem is they will give P value and they will give sigma T value, then ask you compute AT value. Or else the question is maybe something like this also. So I'll ask why M16 a bolt having diameter less than nominal diameter less than 16 mm cannot be used for a fluid tight joints. So I'll ask a question like this. Or else, other way is prove that a bolt having a nominal diameter less than 16 mm is not used for fluid tight joining. Fluid tight joints. So then answer for that. How we can answer that question? He has given M16. So M16 for M16, you need to take the tensile stress area. Due to load due to initial tightening, you need to compute that. From that, you need to compute sigma t value. So then you take the sigma t and compare the sigma t to the allowable stress. Let us say in the previous case, he has given 42 MPa. So now if the stress is more than that 42 MPa means it is going to fail. So then since it is the bolt is having 16 mm or less than 16 mm is failing because of initial tightening, you cannot use these bolts as for fluid tight joints. Like that you can prove it. So without giving numerical values also, they may frame the question something like that. But only thing is, like I already told in the previous class, you have a data book with you, you need to collect all the data pertaining to that particular problem and you need to solve the problem. Okay, so this is about the stresses due to the initial tightening. So even though you have a five types of stresses induced due to initial tightening, we will concentrate mainly on the tensile stress, and we have seen two example problems how we can compute the tensile stress in the bolt due to initial tightening. Then we'll come to the next topic, that is next case, that is stress due to external forces. So far whatever we discussed, those are the, we'll call them as the internal stresses or stress due to initial tightening. Now if external load is applied to a bolt, then what are the stresses induced and how we can calculate those stresses. So generally in case of bolt, the external loads are, one is again direct tensile load, the other one is going to be a twisting moment. So because of direct tensile load, how we can calculate the stress value, and because of twisting moment also, you should know how we can compute the torsional shear stress. Or sometimes both are acting, we have a direct tensile load as well as a twisting moment, both are there, then how will you compute the stresses? In that case, we need to compute the resultant stress and then how we can design the joint also. So these things now we'll see. The first one is the tensile stress, like I said. So the bolt stud screws usually carry a load in the direction of bolt axis which induce the tensile stress in the bolt. So that is nothing but load in the direction of bolt axis, nothing but it is a axial load. If you have a bolt, something like this, so it is subjected to load along the axis. So we'll call it as a tensile load. So because of this tensile load, we have a tensile stress. The formula for tensile stress remains same, P by AT. Whether it is external load or load due to initial tightening, whatever may be the type of the load, but the formula remains same only. So again, you need to take AT from the data book. P here, they will give you the PT value because it is an externally applied load. They will give the P value. Externally applied, what is the magnitude of that externally applied force? So from that, you can calculate the tensile stress. So straight away, you can calculate it. So that is the formula. Individual tensile stress in a bolt is given by P divided by AT, where P is the magnitude of externally applied tensile load. AT is tensile area of the tensile stress area of the bolt. If the external load is taken by a n number of bolts. So suppose in an assembly, this external load is applied to n number of bolts. So that means there are n number of bolts in the connection in the assembly. So this total load is applied to those n number of bolts. Then in that case, what you need to do is, while finding out the stress in each bolt, first you need to compute what is the load taken by each bolt. What is the load taken by each bolt? So if there are n number of bolts and the total applied load P, then load for each bolt is nothing but P by n. Total load is P, and there are n number of bolts. In one bolt, I want to calculate what is the load. So that is nothing but P by n. By assuming all the bolts are taking the load uniformly or equally. So therefore, load in each bolt or load in a single bolt is going to be P by n. So once you know the load is P by n, then the stress is nothing but that P by n divided by AT again. So that is the tensile stress area. So once you know that, you can easily calculate the sigma t value. So therefore, sigma t is for n number of bolts, it is P by n into AT. So right, in case the standard table is not available, then for coarse threads DC is equal to 0.84 D, where D is nominal diameter of bolt. So this is already told there. So but here anyway, so this is not required here. So here to compute this AT, if that is not available, then in that case what you can do is you take this relation DC is equal to 0.84 D and you can compute your AT as 5 by 4 DC square. 5 by 4 DC square. This is done when this AT is not available to you from the data book. If it is available, you straight away pick from the data book. If that is not available from the data book, in that case, what you have to do is you need to assume this relation DC is equal to 0.84 D. So then based on DC, you can compute this tensile stress area. Based on this DC, you can compute the tensile stress area. Once you know the tensile stress area, you can compute the magnitude of the tensile stress also for the given load P. Then next one is the shear stress. Sometimes bolts are used to prevent relative movement of two or more parts, as in case of a couplings. If you take a plain coupling, these bolted connections are used to arrest the movement or relative movement of the two parts. So then the shear is induced in the bolt. Generally, when there is a relative movement between the two parts which are connected to a bolted joint, then bolt will subject it to shear. The shear stress we can easily calculate. Shear stress is nothing but shear load divided by shear area. But generally, the shear stresses should be avoided as far as possible. Generally, because of this external load, we need to design a joint such that the shear stress on the bolt can be avoided. It should be noted that when bolts are subjected to direct shearing load, they should be located in such a way that the shearing load comes upon the body of the bolt and not upon the threaded portion. And also one more point here we need to remember is, if it is not possible to avoid completely the shear stress on the bolt, as long as it is possible to design the joint such that there is no shear stress on the bolt, that is the better practice or good practice. So sometimes it may not be possible, always it may not be possible to make the shear stress zero on the bolted joint. So now in that case, the design engineer has to take care of that. This shear stress is going to act on the only shank portion of the bolt, not on the threaded portion, because threaded portion is going to be the weakest one in the bolt. So the you need to locate the bolt in a such way that the shear load comes upon only the shank portion of the bolt and not on the threaded portion. In some cases, bolt may be relieved of shear load by using shear pins. So here we said we need, our intention is we want to avoid the shear stress in a bolted connection. So one way of avoiding that shear load on the bolted connection is just by using shear pins. If you use shear pins, it will relieve the bolt from the shear stress or shear load. When number of bolts are used to share the shearing load, the finished bolt should be fitted to the remit holes. So reaming. So you have I think you know what is reaming. So if you use remit holes, then the stress concentration will be less. Because of that, the magnitude of the stress is going to be less in case of this in this situation. Okay. So then now still if you follow certain all these things, but still there is a shear load on the bolt, how we can calculate the magnitude of the shear stress? That is, here if you take D is the major diameter of the bolt and N is the number of bolts we are using, the shear load carrying capacity of the bolts is given by 5 by 4 D square is going to be the area of the bolt into number of bolts multiplied by the allowable shear stress in the bolt. You need to take this, then you can calculate the shear load carrying capacity of the n number of bolts if there are n number of bolts. But mind you here, earlier in calculating of torsion shear stress, we use due to initial tightening there we have used DC. But here we are using D only, not DC, because here we are taking major diameter of the bolt. Why we are taking the major diameter of the bolt? Why not the core diameter? The reason for that is already given in the previous slide. So always see here, this is, so it should be noted that bolts are subjected to direct shear load. They should be located in such way that the shearing load comes upon the body, or that is only on the shank. So you need to take the shank diameter. Shank diameter is going to be the nominal diameter of the bolt. So that's why you need to take. Whereas the threaded portion will have a root diameter DC. So we won't use this because the shear load comes on the shank diameter, not on the root diameter. That's why you need to use only D. Instead of DC here, you need to use D. So then this is the formula. Suppose if I know the shear load, if I want to calculate what is the magnitude of tau, I can use the formula. I rearrange this such that I can get a formula for tau also. Tau is equal to PS divided by 5 by 4 D square into N. Or else sometimes I know the number of bolts, I know the PS value, I know the allowable shear stress. I want to determine what should be the size of the bolt. So what should be the nominal diameter of the bolt? I want to calculate the D. So for that also I'll use the same formula here. So in this I know PS, I know N, I know the tau, only unknown is D. Using this relation I can calculate D also. So like that, either way. So you can either it is an analysis or it is a design problem. You can use the same formula to solve it. Then you have the last one is combined torsion, combined tension and shear stress. Combined both, that is tensile load as well as a shear load. If that is the case, then so we already seen the bolt is subjected to both tension and shear load in case of coupling of bolts or bearings. So the example of a bolt which is subjected to both tension as well as a shear stress is a bearings. So then the diameter of the shank of the bolt is obtained from the shear load. That's what we already seen here. The shear stress is calculated based on the diameter of the shank, which is the major diameter. And the previous case, the diameter of the threaded portion is used to calculate the tensile load. So that EAT is based on your DC. So that is calculated. This tensile load is calculated based on DC, whereas the shear load is calculated based on your nominal diameter. So then once you know that those things, you can easily calculate what is the tensile stress, what is the shear stress. So the same formulas. This one for the shear stress formula, and earlier we have seen the tensile stress formula also. Now we need to find out what is the combined effect of these two loads. That is, you have both tension as well as shear. So for that, the combined effect is going to be just you need to find out what is the maximum shear stress and what is the maximum principal stress or maximum principal tensile stress. So for that, these are the formulas. By using these formulas, you can compute the tau max or sigma T max. Then you compare this tau max to your allowable shear stress in the bolt or sigma T to allowable tensile stress in the bolt. So if the allowable values are more than these induced stress values, you can say your design is safe. Otherwise, it is going to fail. That means you need to modify your design and you need to proceed. Okay, so this is about the stress due to external forces. So we will take up 1 or 2 problems on this also in the next class, and then we will go to the combination or combined loads. Okay, those things we will discuss in the coming classes. So I will stop at this point today. We will continue this in the next class. So now I think I already posted that attendance sheet in the classroom. Just respond to that attendance and you can leave the class. Or else if you have any doubt, maybe we'll discuss those. Already 11:30 is now, so we'll discuss in the next class. If you have any doubt, we'll discuss them in the next class. Okay, just respond to the attendance sheet and then you can leave.